So the objective of this lecture is to define the fractal image. So to create an image from scratch, fractal images will be used to illustrate image creation in Java. Also, animation that create an image series of dynamic scene. It adds a new dimension of time to the graphic Java. So Java's multi-threading capability provides support for implementing animations in a Java 2D program. Several examples of animation, including cellular automa, will be introduced. So, as we said before, the source image is usually given as a file in one of many image file formats. An object is created in the Java program to represent the image. The external image file needs to be read into Java object. The image may be displayed in a device such as the screen or printer. The next step is to process the image through one or more image operators like smoothing, filtering, sharpening, transformation, and then the result image is another image object. The processed image that can be displayed on the screen and also can be returned to an external image file. In the last section, we discussed how to create, load, save, process, and display a buffer image. It is also possible to perform low-level operation and directly manipulate the pixels in a buffered image. The raster class encapsulates the pixel data for the buffered image, as we see before, and the writable raster is a subclass that is writable. So to obtain a writable raster object from a buffered image, we may use the get raster. So b buffered image bi equal new buffered image of a certain dimension, and buffer raster equal bi dot get raster. So to obtain a writable raster object from a buffered image, we may use the get raster method. So through the writable raster object, the content of the image can be created at the pixel level. This method of pixel by pixel image generation may be illustrated by the example of building a fractal image. So returning to the raster object that associated with created buffered image, writable raster class contain method that enable to read and update the image pixel. So writable raster w raster buffered image dot get raster. So the method get raster of the class buffer image return the associated writable raster object. The class writable raster can be found in java.awt.image. The raster class provides a number of methods to get pixel data and writable raster method to set pixel data, like get pixel at by using different constructors and set the pixels. The parameters x, y specify the location of a pixel, and w, h, the dimension of a rectangle of a pixel. The data array holds the pixel data. The size of the array depends on the type of the image. For example, if the buffered image is type int RGB, then the data array for each pixel has 3 elements containing the RGB value. So as I said before, the XY, the location, the WH, the dimension of a rectangle of a pixel, and we have the size of the array, and the buffered image contains if the other buffered image is RGB, then the size of the array will be 3 containing the RGB value. Through the writable raster object, the content of an image can be created at the pixel level. This method is pixel by pixel image generation, may be illustrated by the example of building a fractal image. So a fractal image is a self-similar geometric structure. Fracture often exhibits a great deal of complexity, even though they might be generated by some rather simple procedures. A Mandelbrot set is a well-known example of fractals. It is defined on the complex plane. So a complex plane number has the following form: x plus iy. X and y are real numbers, and I is the imaginary value, where I square equals minus 1. The addition and multiplication of two complex numbers, if z1 equal x plus iy and z2 equal x2 plus y2, then z1 plus z2 will be the addition of the real numbers and alone, and addition of the imaginary value, which is y1 plus y2. And multiplication of the two imaginary complex numbers will be x1 x2, I y1 x2, I y2 x1, and I square y1 y2. I square, which is equal to minus 1. Then x1 x2 plus y1 y2, which is complex, and x1 x2 minus y1 y2, and x1 y2 plus y1 x2, which represent the imaginary. The absolute value of a complex number is x plus iy, which is radical to the magnitude of the real plus magnitude of the imaginary, which is x squared plus y squared. A complex number can be interpreted as a point on a 2D plane by identifying the x and y values as a coordinate of a point. The absolute value of the complex number corresponds to the distance of the point from the origin. So to define the Mandelbrot set, we consider the iteration on the complex plane, which is zn plus 1 equals zn squared plus c. C is a complex number, and the starting iteration is z0 equals 0. For a given c, the iteration will produce a sequence of complex numbers z0 to zn. It can be shown that the sequence either tends to infinity or stay bounded. So the Mandelbrot set is defined to be the set of points C such as the iteration is bounded. The Mandelbrot set is complex. It contains recursively self-similar substructures. It is known that the Mandelbrot set is contained in the circle of radius 2 centered at the origin. And if at any step of the iteration the point goes outside the circle, the sequence will escape to infinity, and the corresponding C does not belong to the Mandelbrot set. So for example, if we want to make 5 iteration in the Mandelbrot set defined for C equal I, first, as we said before, Z0 equal to 0. The transformation is Z I plus 1 equals Z I squared plus C. So Z1 equals Z0 squared plus C. Z0 equals 0, 0 plus C, which is equal to I. Then Z1 equal I. Z2, which is Z1 squared plus C, Z1, which is I squared plus I squared, which is equal to minus 1 plus I. Z3, which is equal to Z2 squared plus C, also C as we said before, I, which is I minus 1 squared, I minus 1, which is 1 squared, 1, I squared minus 2I plus I squared minus 1 plus 1 minus 1 cancelled, minus 2I plus I minus I. Z4, which is Z3 squared plus C, and minus I squared from the previous step, plus I minus I squared, which is minus 1 plus I. Then we are returning to Z2. And Z5, which is Z4 squared plus C equal minus 1 plus I from the previous step squared plus I, and the result will be also minus I. Here we can say that C equal I is in the Mandelbrot set. Here, if C equal 1, perform 5 iteration in the Mandelbrot set definition for C equal 1. First, Z0 equals 0. Z1 will be Z0 square plus C, which is 0 plus 1, which is equal to 1. Z2 will be Z1 squared plus C, which is 1 squared plus 1, which is equal to 2. As we can see here, the value is increasing. Z3 would be Z2 squared plus C, which is 2 squared plus 1, which is 5. And Z4 will be 26, and Z5 will be 26 squared plus 1, and then the value will increase. Then C equal 1 is not in the Mandelbrot set. Here is an example that illustrates a way to build an image based on Mandelbrot set. This example creates an image approximating the Mandelbrot set. The iteration process is carried out for each pixel, and the number of iteration is color coded to create the image. So a sample run of the following program will be shown. So the program creates an image depicting the Mandelbrot set in the complex plane over the square x greater than minus 2 and y less than 2. A buffered image is created with the size of 500 by 500 with a RGB pixel type. A writable raster object is obtained, as we can see here, from the image, and the pixel of the image are set through the raster class, raster object. The pixel indices are mapped to the coordinates on the complex plane by a linear function. The iterations are carried out by the method iter count. A complex number is represented by two float variables. The iteration terminates if the values goes outside the circle, which means magnitude 2 of Zn greater than 2. The maximum number of iteration for each pixel is limited to 512. So the iteration count in the range 1 to 512. The complement of the counter max count is used to color a pixel. It has the range 0 to 511. The 9-bit counter value is divided into 3 bit RGB component. So the paint component draws the completed image to Mandelbrot panel, a subclass of D panel, because of the large number of calculations required in generating the Mandelbrot image. It may take a while for the image to appear on the window. So here is the Mandelbrot set colored with the number of iterations. Animation introduces dynamic change to graphic content and often create a visual effect of motion. And animation produces a series of rendered images that depicts the change in a skin. When the frames are displayed consecutively at certain rate, for example 60 frames per second, we may perceive continuous motion in the skin rather than discrete image. Animation adds a dimension of image to graphic model. Each rendered frame at the specific time instance is essentially a regular still image. However, the content of the frames may change over time. Higher frame rate represents smoother animation, but the frame rate of an animation is limited by the capability of the rendering system. So implementing animation in Java usually requires additional threads to handle the time related changes, because an animation typically runs indefinitely. Placing all animation code in the event dispatch thread will make the graphical user interface program not responsive. However, when using swing component to display graphic animation, we need to avoid direct manipulation of swing component from the thread other than the event dispatch thread, because swing components are not thread safe. So, for example, in the animation thread, we should not call getGraphics method and use the graphics object to do graphic painting. There are several methods of swing components that are safe to call from other threads, like repaint and like revalidate. So a proper way to create animation on swing component is to separate rendering from the model change. The rendering code is placed in the paint component method of swing component. The animation logic is placed in the separate thread without actual rendering. When the data for a frame is ready, the method repaint is called a trigger to trigger the rendering of the animation. So as we said, the paint component contains all rendering code to generate a frame. The run method of the runnable interface or the thread class is overridden to perform the animation. It typically contains an infinite loop to continuously generate the frame. Between two frames, the thread typically goes through a sleep period of time. The sleep method of the thread specify a time to time in. So the outline of a typical multi-threaded animation is as follows: paint component to render the frame here, and then the run. While true, we can update the frame and repaint. Try the thread to sleep the indicated sleep time. The sleep method of thread specify a sleep time which is in milliseconds. Here is a simple example of simulated rain. Numerous vertical line segments are moving downward. The location and the length of the segments are random. The sample run of the program output is shown. The class rain panel extend gpanel and implement runnable interface. An array of points to d.double is used to store the location for the lines. There are initialized to random values. The paint component method draws the vertical lines based on the values in the points array and random length. A new thread is created in the constructor of rain to execute the code provided by the run method in the same class. The run method contains an infinite loop that updates line location in the PTS array. Each point is increased by a random amount in the y coordinate, so the line drops down. When a line reaches the bottom, the point is reset to a random location in the top region. After the array is updated, the repaint method is called to redraw the panel. The thread then goes to sleep for 100 milliseconds. An instance of rain panel is placed in the applet rain. A standard main method is included to run the animation application. Here is the completion of the code. As we can see here, we make an infinite loop to update the line location in the PTS array. And here is the output of the rainy animation, as we can see, and you can run it on NetBeans to see the animation. In this example, we have for a complete frame rendering, it takes about 0.01 seconds, and the thread sleep for 50 milliseconds for each frame. We want to calculate the frame rate. The frame time, which is equal to 0.01 seconds plus 50 milliseconds. If we transform it to milliseconds, is equal to 10 milliseconds plus 50 milliseconds is 60 milliseconds. The frame rate is 1 over c, which means 1 over 0.06 seconds, which will be equal to 16.6 hertz. An outline for the timer, as we said before, an alternative to creating our own thread is to use the timer class provided by Swing. A timer object periodically generates an action event at a predefined rate. The event will trigger the listener, which may perform the rendering of a frame. To set up a timer object, we may specify its period and listeners in its constructor and call it start method. As we can see here, timer equaling new timer and the period and the listener, and then timer dot start. The action listener object should implement the rendering in its action performed method, as we can see here. So the timer class provides a more convenient approach for animation than explicit creation of threads, because the action performed method is invoked in the event dispatch thread. it is safe to perform rendering on a swing component in the method.